Alright, big idea here is energy. Energy can change from one form to another without a net loss or gain. This is the main concept of energy. These notes are going to be in three parts. There'll be part 1, part 2, and part 3 for you to watch and take notes on. Energy is a very large chapter. Energy may be the most familiar concept in science, yet it is one of the most difficult to define. We observe the effects of energy when something is happening, only when energy is being transferred from one place to another, or transferred from one form to another, do we actually see it happening. So the first thing we're going to talk about is called work. Work is done when a net force acts on an object and the object moves in the direction of the net force. So when you push on a door and the door opens, you're pushing on the direction that you want it to go, so you're doing work on the door. Work is the product of the force of an object and the distance through which the object is moved. So the quantity force times distance. We do work when we lift a load against Earth's gravity. The heavier the load, the higher we lift it, the more work we do. So if I do this, work is equal to force times distance. If the force is constant and the motion takes place in a straight line in the direction of the force, the work done on the object by a net force is the product of the force of the distance through which the object is moved. So like I said, work is force times distance. Oop, kind of trailed off there. If we lift two loads, we do twice as much work as lifting one load the same distance, because the force needed is twice as great. If we lift one load twice as far, we do twice as much work because the distance is twice as great. If you look at work equals force times distance, the force and the work are directly proportional. If work goes up, force goes up. Or if work goes down, force goes down. Work is done in lifting the barbell. If the barbell could be lifted twice as high, the weightlifter would have to do twice as much work. While the weightlifter is holding a barbell over his head, he may get really tired, but he does no more work on the barbell. Work may be done on the muscles by stretching and squeezing them, but this work is not done on the barbell. When the weightlifter raises the barbell, he is doing work. So lifting the barbell is doing work. Once he gets it above his head and is no longer moving it, there's no longer work being done on the barbell. Some work is done against another force. An archer stretches her bowstring doing work against the elastic forces of the bow. When the ram of a pile driver is raised, work is required to raise the ram against the force of gravity. When you do push-ups, you do work against your own weight. Some work is done to change the speed of an object. Bringing an automobil up to speed or in slowing it down involves work. In both categories, work involves a transfer of energy between something and its surroundings. So, we're talking more and more about work. There's all types of work to be done. The unit of measure for work combines the unit of force, newtons, with the unit of distance, meters. The unit of work is the newton meter, also called the joule. Oops, that's sliding around. Is the joule, because if you remember, a newton was a kilogram meter per second squared, and then we multiplied it by the meter times a meter. That gave me kilograms meter squared per second squared, which is a joule. So work is measured in joules. So the larger units are required to describe greater work. Kilojoules are thousands of joules. The weightlifter does work on the order of kilojoules. Megajoules are millions of joules. To stop a loaded truck going at 100 kilometers per hour takes megajoules. Suppose that you apply a 60 Newton force to a 32 kilogram package, which pushes it 4 meters across a mailroom floor. How much work do you do on the package? Well, since work is equal to force times distance, we have 60 newtons of force and it's traveling 4 meters, so 60 times 4 is 240 joules. When is work done on an object? Think about this. When is work done? When you apply a force to an object, and that force makes it travel a distance, because work is force times distance. Next, we're going to talk about power. Power equals the amount of work done divided by the time interval during which the work is done. So easily put, power is the work divided by time. When carrying a load up some stairs, you do the same amount of work whether you walk or run up the stairs. This is an important concept that usually comes up on quizzes and tests. If you walk up the stairs or you run up the stairs, you're doing the same amount of work because it's the same force going the same distance. What's different is the power rate that you do the work, because the amount of work you do is the same in either scenario, but the time it takes is different. A high-power engine does work rapidly. An engine that delivers twice the power of an engine does not necessarily produce twice as much work or go twice as fast. Twice the power means that the engine can do the work to do twice the work in the same amount of time, or the same amount of work in half the time. A powerful engine can get an automobile up to a given speed in less time than a less powerful engine can. The unit of power is a joule per second, also known as a watt. A joule per second is a watt, or a capital T, is a watt, or capital W, sorry. 1 watt of power is expended when 1 joule of work is done in 1 second. The 3 main engines of the space shuttle can develop 33,000 megawatts of power when the fuel is burned at the enormous rate of 3,400 kilograms per second. That is so fast to be burning fuel. In the United States, we customarily rate engines in the units of horsepower. Horsepower. You've heard that before. And electricity is in kilowatts, but either may be used. In the metric system units, automobiles are rated in kilowatts. 1 horsepower is the same as 0.75 kilowatts, so an engine rated at 134 horsepower is a 100 kilowatt engine. If a forklift is replaced with a new forklift that has twice the power, how much greater a load can it lift in the same amount of time? If it lifts the same load, how much faster can it do this? The forklift that are twice the power will lift the load in the same time, or the same load in half the time. How can you calculate power? Remember, power is the work divided by time, or you could say it's coming up here, force times distance divided by time. That could also be power, because remember, force times distance is how we find work. Alright, now we're going to start talking about the different forms of energy. The first one we're going to talk about is called mechanical energy. Mechanical energy, it's the 2 forms of mechanical energy are kinetic energy and potential energy. Basically KE and PE. Kinetic energy and potential energy. When work is done by an archer in drawing back a bowstring, the bent bow acquires the ability to do work on the arrow. When the work is done to raise the heavy ram of a pile driver, the ram acquires the ability to do work on the object it hits when it falls. When work is done to wind a spring mechanism, the spring acquires the ability to do work on various gears to run a clock, ring a bell, or sound an alarm. So its ability to do work on an item. Mechanical energy. Something has been acquired that enables the object to do work. It may be in the form of compression of atoms in the material of an object, a physician separation of attracting bodies, or an arrangement of electrical charges in the molecules of a substance. The property of an object or system that enables it to do work is energy. Like work, energy is measured in joules. Mechanical energy is the energy due to the position of something or the movement of something. You can think of mechanical energy as the total energy in a system. It's adding the kinetic energy and potential energy together. Whatever combination of these two, that equals your mechanical energy. So what are our 2 forms of mechanical energy? We have potential energy and we have kinetic energy. Okay, potential energy. 3 examples of potential energy are elastic potential energy, chemical energy, and gravitational potential energy. I'm not as worried about chemical energy as I am potential energy, elastic potential energy, and gravitational potential energy. This one I really don't care about that much. An object may store energy by the virtue of its position. Energy that is stored and held in readiness is called potential energy, because in the stored state it has potential for doing work. This is key. It can do work. It has the potential to doing work. That's why we call it potential energy. Elastic potential energy is a stretched or compressed spring has a potential for doing work. When a bow is drawn back, energy is stored in the bow. The bow can do work on the arrow. A stretched rubber band has potential energy because of its position. These types of potential energy are called elastic because something is stretching or compressing. All right, I'll talk about chemical here. Chemical energy in fuels is also potential energy. It is the energy of position at the submicroscopic level. This energy is available when the positions of electric charges within and between molecules are altered and a chemical change takes place. So being able to do work through chemical changes. And this is the main one we use, which is gravitational potential energy. Work is done required to elevate objects against Earth's gravity. The potential energy due to elevated positions is gravitational potential energy. Water in an elevated reservoir and the raised ram of a pile driver have gravitational potential energy. If you lift something up, it then has potential energy up here because it can do work on the way down. The amount of gravitational potential energy possessed by an elevated object is equal to the work done against gravity to lift it. The upward force required while moving at a constant velocity is required to be the weight, mass times gravity, of the object. So the work done in lifting it through a height h is the product, so potential energy is going to be mass times gravity. Oh, it's not letting me write over here. Huh. So the h goes up here. So mgh. All right, note that the height is the distance between some chosen reference level, so as the ground or the floor of a building. The gravitational potential energy, mgh, is relative to that level and depends only on mg and h. So if what they're saying here is if this is ground level, you're going to measure from here and up, not below it, and not above it, not below it, but you're setting a 0 point. It's always important to have a 0 point. The potential energy of a 100 Newton boulder with respect to the ground is 200 joules in each case. The boulder is lifted with 100 newtons of force. Because there's 200 joules in 2 meters, 100 newtons of force. Here, it went 4 meters in 2 meters, 200 joules. In the last one, the boulder is lifted with 100 newtons of force up each of the 0.5 meter stairs. If you look here, across the top, they are all on the same level. So they are the same height. Right? Right? Same height. They're all 2 meters. So they're all at the same potential. They all have the same potential energy. Hydroelectric power stations use gravitational potential energy. Water from an upper reservoir flows through a long tunnel to an electric generator. Gravitational potential energy of the water is converted to electrical energy. Power stations buy electricity at night, and when there is much less demand and pump water from a lower reservoir back up to the upper reservoir, this process is called pump storage. The pump storage system helps to smooth out differences between energy demand and supply. You lift a 100 Newton boulder 1 meter. How much work is done on the boulder? So, work, remember, is force times distance. Oh, I can't write my distance. It's not letting me write distance. So force is 100 times the distance, so you did 100 joules of work. What power is expended if you lift the boulder in 2 seconds? So 100 joules divided by 2 seconds would give me the power, so 50 watts. What is the gravitational potential energy in the lifted position? Well, PE is mgh. Well, mg is going to be your force, which is the 100 Newton boulder. So you have 100 times 1 is 100 joules. Like we just worked on the other page, work is force times distance, 100 joules, 50 watts, and then 100 joules. Name the 3 examples of potential energy. Remember, we had gravitational potential energy. A lot of times you'll see me write it as PEG. You have elastic, PE. I usually write like elastic or E or something on the bottom here. And then we had chemical potential energy.